So, welcome everyone to one more edition of our student algebraic geometry and foliation seminar at INPA. Today, it's again a pleasure to introduce an old colleague at INPA in the course of algebraic curves, and now we are PhD colleagues in the mathematics in the world. And so, this colleague took the masters here at INPA, and now he's taking the PhD at the Emory University under the supervision of the professor David Zurich Brown. And today he will talk about zeta functions and the Weil conjectures. So feel free again at your old environment.
Muito obrigado, Eduardo, pelo convite. Obrigado a vocês por vir. Minha palestra, hoje eu vou falar em inglês. Ideal seria fazer como o Rob Morris e escrever em inglês, falar em português, mas eu conheço bem as minhas limitações. Yes, today I'm going to talk about zeta functions and the Weil conjectures. This is one of the jewels of arithmetic algebraic geometry, and probably some of you are familiar with them, but just to start with something familiar to everybody, let's talk about the Riemann zeta function. Great. So yeah, you have probably seen the Riemann zeta function before, defined to be the sum of reciprocals of the integers to some complex power. And the fundamental theorem of arithmetic is equivalent to the fact that you can actually write it as an infinite product over the primes. Let me rewrite this first product a little bit differently. So instead of counting over primes, I'm counting now over maximal ideals in Z, which is the same thing because our ring is a principal ideal domain. And P is also the size of this quotient ring, Z mod P. Here I have a -1. So let me rewrite this once again. Now I want to look at it as close points on my scheme spec of Z. So I'm going to denote the close points of a scheme by bar. So I'm counting points, 1 minus the size of the residue field to the minus s to the -1. For what kind of schemes can I do the same thing? So it turns out that there's a very general class of schemes for which this definition works. So the only thing I need is that for closed points, the residue field is finite. So let's define an arithmetic scheme to be a scheme of finite type over Z. And yeah, for arithmetic schemes, we have this property. For every closed point, the residue field is finite. And we call it the norm of the point. So some important examples of arithmetic schemes are the spectrum of the ring of integers of some number field. So spec of Z, or say spec of the Gaussian integers. And a second important class are varieties over finite fields. So solutions to polynomial equations over some finite field. And for an arithmetic scheme, we define the zeta function of x to be the product over all closed points of 1 minus the norm to the minus s inverse. Today I'm not going to focus on any convergence issues, but this turns out to be holomorphic function defined for when the real part of the complex variable s is greater than the dimension. So for Z, we had that this other product converged on the half-plane real part of s greater than 1. But more generally, it's always going to converge on some open plane. Great. So before looking at some examples, let's notice two properties that fall basically from the definition. So the first one is that I can only consider reduced varieties and I don't lose any information. And the reason, as you probably know, is that, well, as topological spaces, a scheme and its reduction are homeomorphic. They have the same set of closed points. So since the zeta function is something that only depends on the set of closed points, this is true. Secondly, if I can write my scheme X, or the closed points of my scheme, as a disjoint union of closed points of subschemes, then my zeta function is going to be the product over the zeta functions of this disjoint union. Maybe one thing to notice here is that this product, of course, might be infinite. This is already the case when we take X equals spec of Z. But just because X is an arithmetic scheme, this product is always going to be countable, which is maybe not obvious. All right, so let's look at some examples. So the easiest possible example, which is going to be important for us today, is when we take just a point. So let's look at the spectrum of a finite field considered as a variety over FQ. So the ground field is always important for us. So just by definition, since we only have one closed point, this product has only one term, and this is the size of the rest of the field, just because we're looking at my scheme as a scheme over FQ. And just a hint to what's going to happen next, if we take change of variables and we write t for q to the minus s, then I can write this as 1 over 1 minus t to the n. And this is a rational function in t. So the example we saw above, let's recalculate it differently just using the definition. So we can write the closed points of z as just a disjoint union over all primes, right? And the zeta function of the scheme spec of z coincides with the Riemann zeta function. So that's good. People in the audience like number theory, you've probably heard of the Dedekind zeta function. And that is just the zeta function of the scheme spec of OK, where OK is a ring of integers of a number field K. So these two zeta functions are like the center of some of the most important conjectures in number theory, the Riemann hypotheses, the generalized Riemann hypotheses. So yeah, moving on, let's look at another example that it's not a point. So let's look at a one-dimensional variety, the simplest one, A1. Yeah, what's interesting about A1 is that, well, as you know, this is the spectrum of the polynomial ring in one variable. And the polynomial ring in one variable has a lot of properties very similar to the integers. It's also a unique factorization domain. And we can basically repeat the proof for the Riemann zeta function and the Euler product. And what we end up getting is that we can write the zeta function of A1 as sum when I'm counting the number of Molic polynomials of degree d, which they are very easy to count. It's just count coefficients. And since I have d coefficients and q possibilities for what the coefficients can be, this is this infinite series, which just using a geometric series, I can write like this. And once again, doing a substitution, t equals q to the minus s, I can again rewrite this as a rational function. So great. Let's now look at another example of something that is not affine. P1. So P1 is smooth and projective, and I can write it as a disjoint union of the affine line and the point at infinity. So I can use the property number 2, right? And since I already calculated the zeta function of A1 and the zeta function of a point, well, the zeta function of P1 is going to be the product of both. And again, doing the substitution, I can write this as a rational function. Any questions so far? I'm happy to answer questions in Spanish or Portuguese or English. All right.
Just a question. So this spec of F key you are identifying with the infinite point, right? So because I haven't seen this association of P1 as the union of the spec of the polynomial ring in one variable and spec of F key and wow, yeah. And so I can apply that property that you have mentioned.
Yeah. So basically, when you take P1 and you choose some coordinate system such that this is proj of FQ of x, comma y, right? Choosing some affine patch, so saying y different from 0, that gives you that you can write this as some open subset, which is spec of FQ of x over y, and then you have the close point corresponding to y equals 0. So that's what I'm calling infinity.
Okay, perfect.
Is the usual, yeah, the usual. I mean, you can construct P1 in many different ways, but if you take away a point from P1, you get the affine line. So another way to think about this is, yeah, what are the close points in A1? Well, they are irreducible polynomials, irreducible monic polynomials. This is by choosing a variable t, and the point at infinity corresponds to the polynomial 1 over t. Okay. So yeah, now we're going to focus on varieties over a finite field, which are the topic of the Weil conjectures. So as you noticed before in all of our examples that were varieties over finite fields, we ended up with some rational function in terms of q to the minus s. So just to make things a little bit more transparent, let's make this change of variables once and for all. And instead of calling it zeta with the Greek letter, we're going to call it with capital Z. So just redefining the zeta function with our slightly different notation, we define zeta of our scheme of our variety x and the variable t to be this infinite product. And yeah, recall that the degree of a point is just, well, since my residue field is a finite extension of my ground field, I can take the degree of that extension, the dimension of the residue field over FQ as a vector space. And we're just going to think about this zeta function as an element and in the ring of formal power series with rational coefficients. So we're not thinking about convergence or analysis right now. This first proposition is really surprising and very interesting. So if you take your zeta function for any variety, it doesn't have to be smooth or projective, then you can recover it as certain generating function just by counting the number of points over extensions of my ground field, right? So imagine that x is defined by some polynomial equations, and you count the number of solutions in FQ, then you count the number of solutions in FQ squared and FQ cubed and so on. And you plug all those numbers into this weird looking generating function. Well, you get the zeta function that we've been talking about. And yeah, just recall that the exponential of a given power series is the power series that you would expect. So let me check my time. Okay, it's been 20 minutes. We have time for the proof. Any questions before I discuss the proof? Okay. So let's denote by ND the number of points of a given degree D. And let's call GFQ the absolute Galois group of my ground field. And as you know, the Galois group acts on the solutions on FQ bar. So this is basically, if you have a polynomial equation, you can slap it with your automorphism, and since the coefficients are defined over FQ, if you have a solution, the conjugate is also going to be a solution. And this is the action that we have here. And the key ingredient of this proof is the fact that, well, you can look at a close point, either taking an affine patch and looking at a maximal LD on that affine patch, but that is the same thing as taking a Galois orbit of a given point over the algebraic closure. Right, so just using this fact that a point of degree D is going to be a size D orbit of the action of the Galois group on my geometric points, then I can write the points in Q to the R as a disjoint union of all the points of degree D defining R. And this gives you this interesting convolution formula for the number of points. So it's basically over all divisive of R, you multiply D by the number of points of degree D. And that gives you the total number of points. So we're just going to take this formula and plug it into the generating function that we have here. Well, actually the logarithm of the generating function, so what's inside. Okay, so if we do that, we start here, we plug in our formula inside of this part. That's what's in parentheses in here. And this is this really surprising thing about analytic number theory, that everything boils down to changing the order of the sum somehow. So once you change the order of the sum, you get the sum over here. And now you recognize that this side looks like the Taylor series for the logarithm. So that's exactly what it is. And the logarithm, formal logarithm of power series can be pulled out of an infinite sum, and we get an infinite product. And yeah, just rewriting this, we get the definition of the zeta function. So great, now we have another tool for calculating zeta functions. Basically, if we know the number of points for variety over extensions, we can plug it in, use this formula, and get the zeta function. Yeah. Are there any questions? So an interesting problem for you to think about, if this is the first time you see this, is calculate the zeta function of projective space, something higher dimensional. So far we've only seen examples in dimension 1 or less. And the good thing about this is that we know the point count of projective space, right? We know that the number of points of p to the n over fq over some field extension. So fq, did I call it r? Yeah. This is going to be, well, this is basically lines in n+1 dimensional affine space, right? So this should be q to the r to the n+1 minus 1 and mod fq star. So fq star has q to the r minus 1 points. So you know the point counts for projective space, plug this into this formula, and you get the zeta function of projective space. All right. So we are finally getting to the Weil conjectures. I'm gonna start revealing each one of the conjectures one by one. So we start with a variety over a finite field, FQ. The first conjecture is something that you might just conjecture yourself just by looking at the examples so far, is that the zeta function is always going to be a rational function with rational coefficients, which is definitely not the case for the Riemann zeta function, for example. The second conjecture is that when our variety is smooth and projective, then we can factor a rational function in this form. So we have the terms of odd degree upstairs, terms of even degree downstairs. These are all polynomials with constant coefficient equal to 1. And over C, these polynomials factor like this, and the roots are in a given circle. So for the pi polynomial, the roots are all lying on a circle of radius t to the I over 2. And maybe a good question for you to ask later is, why is this called the Riemann hypothesis? The third conjecture is that, as the Riemann zeta function does, these zeta functions for varieties also satisfy some sort of functional equation. So as you know, the Riemann zeta function can be extended to a meromorphic function on the complex plane, and there is this symmetry between the points on the right hand side of the real part equals 1 and the points on the left hand side. You might have noticed that I suggestively called the degrees of these PIs to be BI for Betty numbers, and associated to our variety, we have something called the Euler characteristic of our variety, which is going to be the alternating sum of these degrees. So this is this term appearing here and here. D is the degree of our variety. Furthermore, if X is geometrically irreducible, then we know what P0 and the top degree polynomial should be. And finally, and probably the most surprising one, is a relation with topology, with singular cohomology. So say you start with a variety not defined over a finite field, but over some number field. Fix an embedding of your number field into the complex numbers. So what you can do now is take the equations that define your variety and reduce them mod given primes. Then you have a variety defined over a finite field, and you can look at the information given in the previous step, right? So you have these BIs for each one of these reductions. And another thing you can do with your original variety is, instead of looking mod primes, is looking at the complex points, right? Then you get some complex variety, and you can calculate the singular cohomology with integer coefficients of that variety. And the surprising thing is that somehow the degrees of these polynomials know about the cohomology of the complex variety. So it's somehow this really deep relationship between the arithmetic of your variety and the topology, the classic complex geometry of your variety. Yeah, so instead of writing down everything twice, I was thinking about showing you some pictures that I have in a blog post that is on my website. If you want to read it, go ahead. I wrote it for myself, but also for this presentation. So let's look at the last item, maybe beforehand. This is a mouthful. There's a lot of conjectures here, so I bet there are questions or yeah. Should I talk a little more about something, or are there any questions?
Santiago, I have a simple question. So, could you repeat what are these initials BIs when you are defining the Euler characteristics? Because I was imagining that they would be the bad numbers or something like that. Could you repeat what they are?
Sure. Yeah. Right
So
now, I'm just defining them to be the degrees of these polynomials pi.
Sorry.
So yeah.
Okay. Okay.
What this part of the theorem tells us is that the zeta function is a rational function, and we're gonna have certain polynomials, right?
Okay.
So bi is the degree of the polynomial pi appearing in this factorization.
Okay. Okay. Thank you. Thank you.
But yeah, you're kind of spoiling what I wanted to say next, which is there is actually some cohomology theory for which this bi is a Betti number. It's a dimension, the rank of some cohomology group. Yeah, great question. All right, so maybe to fix ideas, let's look at the simplest case to see what the conjecture, the singular chromology part of the conjecture says. Oh, by the way, I didn't mention, but the Weil conjectures are called conjectures because of historical reasons, but they are now theorems. They are proven. I'm going to say a little bit more about the history of the proof in a minute. So let's look at the example of an elliptic curve, right? So let's say our variety is given by this equation here, right? So I have the equation y squared plus y equals x cubed minus x. This is a nice curve. If you go to this link, it takes you to the LMFDB, and there's all the information that we humans know about this elliptic curve. So you can look at the minimal equation, the rank, the conductor, discriminant, J invariant, whatever invariant you're interested in, you're going to find it here. In particular, the discriminant of this elliptic curve is 37. So if we pick some prime not dividing 37, we can reduce this equation mod that prime, and we get another elliptic curve now defined over a finite field. So yeah, here's a graph of the real points of our elliptic curve. Now, I chose the prime 1013. So if you take our curve and reduce it mod 1013, you get the curve y squared plus y equals x cubed plus minus 1 in this field is 1012. So we get this curve. And we can look at the number of solutions. We can even graph the solutions. So you can do this in Sage. And you get this picture, which at first seems kind of random, but then you notice that there's a symmetry. So yeah, this is a plot of points over f 10,013. 1013, sorry. And what the singular chromology part of the conjectures tells us is that this graph, or more precisely, the number of points over every extension of F1013 knows that the graph over the complex number for elliptic curves actually looks like a torus. So the arithmetic knows about the topology. So let me say a few things about the proof. A lot of people worked in these conjectures. They were first proposed by André Weil, and Weil proved the conjectures himself for curves of arbitrary genus and abelian varieties. Before that, Schmidt proved the statements for elliptic curves, for curves, except for the Riemann hypothesis part. And Hasse proved the conjectures for elliptic curves. So they not only proved the conjectures and proposed them in several cases, but he also proposed a strategy to prove them. And the strategy comes from topology. So it's something called the Lafayette's fixed point theorem. And it says something like the following. If you take some d-dimensional compact real manifold and you look at a function of the manifold onto itself in some reasonable map, so let's say it's differentiable, then you can look at the induced map in singular chromology, and what this fixed point theorem tells us is that you can count the number of fixed points by calculating this alternating sum of the traces of the induced function on each degree I cohomology. And what they notice is that, okay, now in the case of some variety over a finite field, you have some endomorphism of your variety, which is the Q power Frobenius. And the number of points, it's actually the fixed points of Frobenius. So if there existed some cohomology theory, of course not singular cohomology, it's really hard to triangulate some variety over a finite field, but some cohomology theory in which you could have Frobenius acting, then there might exist some Lefschetz fixed point theorem analog in this world over a finite field, and you could get the conjectures via this cohomology theory. This actually turned out to be true, but before, in surprising everybody, Dwork proved the rationality part of the Weil conjectures using elementary p-adic methods, so no cohomology. And for the rest of the conjectures, a lot of people, but perhaps most notably Artin and Grothendieck, developed the theory of étale cohomology. And they proved the Lefschetz fixed point theorem for these types of varieties. So in the number of points over FQ can be calculated as this alternating sum of the trace of Frobenius acting on étale cohomology. And this formula allowed them to prove the conjectures, the first three conjectures, except for the Riemann hypothesis that was perhaps the hardest part. And this was finally settled by Pierre Deligne. If you want to read more about the proof of the conjectures and the history, I have a link for a really cool brief history in my blog. Yeah, one thing that I remember reading, but I can't seem to, I think I lost the reference, is that before topologists knew what the Betty numbers of Grossmannians were, they, using his conjectures, calculated just by counting points on the Grossmannians over finite fields, and told them like, hey, are these the Betty numbers of Grossmannians? And nobody knew, but he turned out to be correct. Yeah, the last thing I want to say today is that I want to try and prove the conjectures at least in dimension 0. So this should be the simplest possible case. Before I jump in, are there any questions? All right. So yeah, let's start with some variety x defined over a finite field fq. And let's suppose that our variety has dimension 0. Well, first thing we know is that our variety has to be finite. It has to have finitely many points. There are many ways to see this, but maybe one way to prove this using a bazooka is use Serre's criterion for affineness and growth and dick vanishing. I think Eduardo talked about this theorem a couple weeks ago. Then using those two bazookas, you can show that, well, first of all, your variety has to be affine, and its dimension 0 has to have finitely many points. But yeah, I'm just going to say for now that it is well known that X has to be at the joint union of the spectrum of Artinian FQ algebras. And so, for example, one of the components can be this reduced ring, right? So I can have the equation t squared equals 0, which is a single point, but this is a reduced variety. The good thing is that, well, the Weil conjectures are statements about the zeta function, and zeta functions only cared about non-reduced varieties. So we might as well just assume that X is reduced, and in that case, well, we can write X as a finite union of finite fields. And by property 2, we only need to verify the conjecture for one of those, because yeah, this is not difficult. If you have the conjecture for finite fields, then, well, the rationality is going to follow, the functional equation is also going to follow. So yeah, we're going to focus on the case that X is just the spectrum of a field. So remember that we're considering this as a variety over FQ. So this is an example. Of course, this variety is reducible, but it's not geometrically irreducible, right? If you base change to FQ to the end, then this is going to be endpoints. So great, this was our first example. We already calculated the zeta function. So we know that zeta of x is this nice rational function. So the rationality part of the conjectures is satisfied. Secondly, remember that the conjectures asks us to prove that this is going to be some quotient of polynomials where the things of odd degree are in the numerator and the things of even degree are in the denominator. But we can see from here that, well, we don't have any polynomials on top, and we also don't have odd dimensions. So that is what we expected. And this is our polynomial P0. So this polynomial is really nice. We know how to factor this polynomial. This is the negative of we can factor this polynomial very easily by taking some primitive at a root of unity. So these roots, of course, satisfy the Riemann hypothesis, because if you take, well, the size of the roots, this is 1, they all lie in the circle, which is the same thing as 0 over 2. So this is this part of the conjectures, the fact that the roots lie in a given circle. And here I is equal to 0. So great. We've verified both rationality and the Riemann hypotheses. The functional equation is also easy. So notice that here the Euler characteristic, since we only have one polynomial, is going to be equal to b0. And b0 is the degree of this polynomial, which is n. So this is the functional equation that we need to verify. But here d equals 0. So this is replaced by 1. This gets replaced by 1. And this gets replaced by t to the n. And just by plugging 1 over t, we get this function, which of course multiplying by t to the n on the top and on the bottom is the same thing as this. So yeah, the functional equation is satisfied. And finally, the hardest part of the conjecture, maybe just say a couple of words about it, is the relationship with singular chromology. So for this, we have to get a little technical and, well, define what does it mean to get a model for our variety, and what does it mean for our variety to have good reduction of a given prime. But in this particular case, a smooth projective variety over a number field has to be just the spectrum of a number field containing my base number field. And this boils down to a problem in algebraic number theory. A prime of good reduction is going to be an unramified prime. And yeah, the complex points of the spectrum of a number field are just the embeddings of my number field into C. So I have n of them. The h0 of a finite set is just going to be the number of points. So it's n. And the fundamental identity from algebraic number theory is going to give you that the degree of the reduction has to be n as well. So it's kind of neat that the singular chromology part of the Weil conjectures turns out to be a problem in algebraic number theory. Yeah, and that's all I had to say for today. But before, are there any questions?
Okay, if there are no questions for this moment, let's thank the speaker. Let's thank Santiago for this talk. Did you finish?
Yeah.
Yeah, okay, so let's
Thank
talk.
you.
Let's thank, sorry.